Okay, let's get started with this. So actually, I want to start off with a kind of warm-up exercise. Warm-up exercise. So you have two matrices, A and B. They're the same size. And B is actually equal to S inverse AS. Right? So B is conjugate to A. Okay. And X is in the eigenspace of B. So I'm going to use, I hope this is kind of obvious notation. It has an eigenvalue, it's an eigenvector for B. It's an eigenvector for B with eigenvalue lambda. Right? In other words, Bx equals lambda x. Right. Okay. So pretty straightforward. I'd like you to show that Sx is an eigenvector for A with the same eigenvalue. If you know what you're doing, this should take you like 30 seconds. Okay, turn to a neighbor and tell them what you're doing. Okay, so this is mainly just like a vocabulary problem, right? Like, do you know what we're saying, right? You want to show that Sx is in the eigenspace for A with eigenvalue, with eigenvalue lambda, right? What does that mean? That means that you want to show that A Sx equals lambda Sx, right? Okay. It's just a translation, right? Okay. So in other words, you want to show that. Right? And you know that Bx equals lambda x, right? This is what you know, right? That Bx equals lambda x. But remember, B is S inverse AS, right? So how do you get from here to here? You multiply, multiply by S, right? So just multiply on both sides by S and you're done. Right? You know this, which is the same thing as this, and that definitely implies this by just multiplying this thing. So right, multiply by S on the left, right? You get these guys vanish, you get ASX equals S lambda x, but you can pull the constant through the matrix, of course. Done. Okay, here's something that I was going to give as an exercise, but I've got a big X next to it, indicating that I should not give this as an exercise. So let me just explain it. Okay, so theorem. If you have two square matrices, A and B, and suppose again that B equals S inverse AS. Then the characteristic polynomials are the same. The characteristic polynomials are identical. Okay, and the proof is Well, the characteristic polynomial for B, let me call that P sub B lambda, P sub B of lambda. We know that that is the determinant of B minus lambda I, right? That's what the characteristic polynomial is, right? Well, again, B is S inverse AS. So, right, we want to relate this back to A, and we do something funny at this point, which is we rewrite the I as S inverse lambda I S. So we just do some algebraic trickery. Okay, and then you rewrite it again, S inverse A minus lambda I S. Right, so you distribute out more algebraic trickery, right? And then you see what we have here. This is going to be determinant of S inverse times the determinant of this times the determinant of S. Those guys, the first and last terms will cancel, right? Because the determinant of S inverse is 1 over the determinant of S, and so we just end up with the determinant of A minus lambda I, which is the characteristic polynomial for A, right? So the characteristic polynomials are the same. So what does that tell you? That tells you that the eigenvalues of similar matrices are identical, right? The characteristic polynomials are identical. In other words, the eigenvalues are the same. Okay, and what this one is telling you, I guess this is another way of seeing that, right? Look, these guys are similar matrices. If this is an eigenvalue for B, well, it's going to be an eigenvalue for A also, right? So this is kind of an alternate way of seeing the conclusion of that, right? And it's also telling you, if you think about it, it's also telling you that the dimensions of the eigenspaces are going to be the same as well. Okay, so yeah, actually the dimensions of the eigenspaces are going to be the same because you're using an invertible matrix. You're using an invertible matrix to get from one to the other one, right? That invertible matrix gives you an isomorphism. But anyway, don't worry too much about that. We'll yeah. But it's true. Okay, so I'm just going to go on into the next section. So I know that I said I was going to do the last the trace. Remember, we still wanted to prove that thing about the trace, but I made at the very end of the video, I just recorded 4 more minutes. Watch those 4 minutes, and then so we can just get on to diagonalization. So yeah, rather than having to reset the whole thing, that'll just take much more than 4 minutes. Okay. So and I'm sorry, I forgot to tell you that I was going to skip 6.2. So we're going to go right into 6.3 diagonalization. If you read 6.2 in preparation for the lecture, I apologize. Okay, so diagonalization. So Okay, so we're going to start off with the following. If you have an n by n matrix, and suppose that there are that lambda 1, lambda 2 to lambda k are distinct eigenvalues of A. Okay, so none of these are equal to each other. Okay, and suppose that v1 to vk are eigenvectors corresponding to lambda 1 to lambda k respectively. Okay. So v1 is an eigenvector of lambda 1, v2 of lambda 2, and so on and so forth. Okay. Then the vi must be linearly independent. The vi are linearly independent. Okay. The main thing what we're going to use this for is the corollary. So this theorem implies a corollary, which is that again, if you have a square matrix, and if A has n distinct eigenvalues, then what? Write down, take 30 seconds and write down something. Okay, turn to a neighbor and say, this is what I wrote down, or this is what I think is the conclusion. If A has n distinct eigenvalues, then blah, blah.
I think, but I could be wrong. I could be.
Okay, that's what I was thinking, kind of, but simpler.
Okay, anybody want to say what they think is the conclusion? Other than Izzy? No? Okay, go ahead, Izzy.
Does it have n distinct eigenvectors?
Yeah. So what does that tell you? You've got n distinct, well, sort of, yes, for sure. And?
Oh, and it's it doesn't span A? Does the eigenvector span A?
Not A.
Or the range of A?
But it'll span Rn, right? So you're gonna have n linearly independent, right? N linearly independent vectors. N linearly independent eigenvectors. Well, that's enough to span Rn, right? So in other words, what you have is you have a basis of eigenvectors. You're guaranteed a basis of eigenvectors. Okay, and that's a good thing. That's desirable. That's desirable. It basically says that your matrix is very simple. Okay, let's prove the theorem. We don't need to prove the corollary that follows immediately, right? You just say it follows immediately. Okay, so proof of the theorem. So we want to show that want to show that the v sub I equals 1 to k, are linearly independent. Oops. Okay. So, so what we're going to do is prove by contradiction. So suppose not, right? Say that the dimension of the span of the VI is actually strictly smaller than k. Okay, so they're not independent, right? If they were independent, then the dimension should be k. The dimension of the span would be k, but it's strictly smaller than k. So let's say that the dimension is r, and r is some number that's smaller than k. Okay. So without loss of generality, let's say that v1 to vr are linearly independent. But if we throw in one more guy, if we go up to r plus 1, then these guys are dependent. Okay, so is that all right? Right. So, suppose the span has dimension r. Take the guys that have that span and make them the first r. There was no guarantee that they were actually 1 through r, but let's relabel them so that those guys are 1 through r, so that the linearly independent guys are v1 through vr. Okay, that's why I say without loss of generality. We can just relabel. Okay, so relabeling. Those guys are linearly independent, and we throw in one more. They're linearly dependent. So they're linearly dependent. So that means that there exists C1 through CR plus 1, not all 0, such that C1 V1 plus C2 V2 plus CR VR plus CR plus 1 VR plus 1 is the zero vector. Definition of linear dependence. Okay, so we're going to multiply everything by a. Multiply by a. We get, C1 AV1 plus C2 AV2 plus CR AVR plus CR plus 1 AVR plus 1 equals 0. Okay. Let me note that one of the C1 through CR must be non-zero. So in particular, right? We know that that these guys cannot all be the coefficients cannot all be 0. Right. In particular, one of these initial guys' coefficients must be non-zero, because if they're all 0, that would mean that CR plus 1 VR plus 1 is equal to 0. But that would mean that this is 0, and then all the coefficients would be 0. Okay. In any case, just believe me. Okay, but this one of these initial guys must be non-zero. Okay. Okay. So then you multiply everything through by A, and you get, of course, C1 lambda 1 V1 plus C2 lambda 2 V2 plus CR lambda R VR plus CR plus 1 lambda R plus 1 VR plus 1 equals 0. Okay, it's a lot of writing, but little bang for all that writing. Okay, so now we're going to take this thing here, and we're going to multiply it by lambda R plus 1. Okay, so we get C1 lambda R plus 1 V1 plus C2 lambda R plus 1 V2 plus CR lambda R plus 1 VR plus CR plus 1 V lambda R plus 1 VR plus 1 equals 0. I actually kind of dislike this proof. It's a lot of work and little reward for it. Anyway, so you take this thing, take this guy, and multiply by lambda R plus 1. That's all that happened. We just took this thing up here, which we got from the dependence, right? This thing we got from the dependence, multiplied by R plus 1, and then we're going to subtract. Yeah.
What happened to the lambdas from the thing before? It's like basically the lambda sub I become lambda sub R plus 1.
So this is another line of reasoning, basically. So from here, we multiply by A through A. We got the different lambdas,
Yeah.
right? We also start from here, and we just multiply this thing by lambda R plus 1.
Oh, okay, so they're different things.
Yeah,
Okay.
yeah. So now we take this thing, we multiply it by lambda R plus 1. We get that, right? So
Yeah.
right now we've got, C1 lambda 1 V1 plus CR plus 1 lambda R plus 1 VR plus 1 equals 0. And we also have the same statement, but not with different lambdas this time. The same lambda that we just multiplied the whole thing through by that same lambda now. Rather than multiplying by A, we multiplied by lambda. Okay, and then we subtract. Okay, subtract the guys. What do you get? You get C1 lambda 1 minus lambda R plus 1 V1 plus CR lambda R minus lambda R plus 1 VR plus 0 equals 0. Right, because these last guys are identical. Right. Those last guys are identical, that's why we get that 0 at the end. Okay, so what do you see? You see that you have a linear combination of the V1 through VR that gives you 0, right? And these guys are not all 0, right? These coefficients are not all 0, right? Because remember, for the C1 through CR, they were not all 0. Right? C1 through CR were not all 0. The eigenvalues are all different, right? So all these differences are non-zero, right? So that means that the new coefficients are not all 0, right? The new coefficients are not all 0, so that tells you that V1 through VR are linearly dependent, right? But that's a contradiction. V1 through VR were actually linearly independent. So coefficients not all 0, so we get that V1 through VR are linearly dependent. contradiction. Sean, you look like you have a question. Do you have a question?
I'm just thinking about it.
Okay. Okay. So this proof, unfortunately, once you start doing proof by contradiction, because you enter a world where you're trying to show nonsense, right? So it's kind of a weird thing. It would be much better, and I think in my notes I see I've started to write out like there's a better don't do it this way, do it some other way. So we're going to do proof by contradiction. We say we want to show these guys are linearly independent, right? Suppose they're actually dependent. If they're dependent, then we can end up with this nonsense. So if they're dependent, we have this statement, right? Some linear combination of them will be 0. Hit that thing with the transformation. So multiply that thing by a, and we get this one right here. Okay. But at the same time, if we multiply this thing not by the matrix, but by a constant, then we get this one. Then we get this statement. When you subtract those two statements from each other, you end up with a dependence between the original V1 through VR, which is impossible. Is it?
If you were to, I'm just kind of confused because let's say instead of like saying the dimension's equal to R, if we said it was equal to K, like and we said it was linearly independent, we're proving that, where in the proof would it not contradict itself? You know what I'm saying? Instead of saying it's some dimension that's less than K, if we said it was K.
But that's what you're trying to show, right? You're trying to
Okay.
show that the dimension is K. You can't start from that as your
Gotcha.
as the thing you're. That
Okay.
can't be your. So proof by contradiction, you assume that what you're trying to show is false,
Okay.
right?
Yeah.
But but you definitely can't start by assuming what you're trying to show is true.
Okay.
Right. That's not how. Yeah. So assume that what you're trying to show is false, and then try to end up with nonsense.
Okay.
Yeah, it's strange. Okay. Okay, I'm going to let's go on. Let's go on. I think that's like I said, the effort put into this proof is nowhere near worth the result that we get out of it. Okay. Okay. So here's an important definition that's kind of trivial. You have a square matrix. If there exists an invertible matrix X such that X inverse AX is diagonal, then we say the matrix A is diagonalizable, or sometimes people just shorten that to diagonable. Okay, and that A is diagonalized by X. Okay, so it just means that A is similar to a diagonal matrix. Right. Remember when we were talking about linear transformations, we said that each linear transformation actually corresponds to a whole equivalence class of matrices, right? So, this this x inverse AX is just something in that equivalence class. So you've got your matrix, you've got, this is equivalent to that, it's similar to that, and it happens to be diagonal. So what it's saying is basically that your matrix is actually more complicated, more simple than it looks. Your matrix is more simple than it looks. It's actually, as long as you change your bases in the right way, you're going to get a diagonal matrix. Your linear transformation is simpler than it looks. I'll say that more clearly in a second, but before we do that, let's do something pretty straightforward, which is that A is diagonalizable if and only if A has an eigenvector basis. Okay. In other words, an linearly independent eigenvectors. Okay, so A is diagonalizable if and only if you can find n vectors, if you can find a basis that consists entirely of eigenvectors of A. So let's do the proof of this. Okay, let's do the backwards direction first. So suppose B1 through Bn is a basis of eigenvectors. Suppose you have a basis of eigenvectors. Okay. Let capital X denote a matrix with those guys as the columns. B1, B2, Bn. Okay. Now, consider A times X, right? So it's A times the matrix of these columns. Okay. If you remember how a matrix acts, it's going to multiply each of those columns separately, right? So this is going to be AB1, AB2, ABN. Right? Right. But remember, those guys are eigenvectors. Maybe put some notation with say eigenvalues lambda 1 through lambda n respectively. Okay, so now I can write down what this is. This is going to be lambda 1 b1. Second column is going to be lambda 2 b2, et cetera, lambda n bn. Which I'm going to rewrite as b1 through bn times the diagonal matrix lambda 1, lambda 2, lambda 3 through lambda n. Okay, I hope that's clear that when you multiply these guys together, this is what you're going to get, right? Right? The lambda 1 is only going to affect the first column, the lambda 2 is only going to affect the second column, and so on and so forth. Okay, so what do you see? You see that, right, so it's bad board work, but let me just go this way. What you see is that AX equals X times the diagonal matrix. Right? In other words, x inverse AX is diagonal. Right? So so A is diagonalizable by X. Oh,
So like if you know the eigenvectors, you can figure out the eigenvalues based on this.
that's true. Yeah. So if you, yeah, that's true. Um, okay. Okay, everybody okay with that? Right? Okay, so that's the backwards direction, right? If you have an eigenvector basis, right, then your matrix is diagonalizable. Now let's do the forwards direction. Right. So part 2, forwards direction. Assume that your matrix is diagonalizable. So say that for some invertible matrix X, X inverse AX is D, which is diagonal. Okay, but then what does that tell you? That tells you that AX equals XD. Very good. Yes, right, and then that's the end, right? That's the end right there, right? Because you see that A times the first column, xn, is going to be, you know, x1 through xn times some diagonal matrix d1 through dn, right? But as we saw before, this left-hand side is just ax1, ax2, axn, and the right-hand side is just d1 x1 through d1 xn, dn xn. Excuse me. Right, so we're basically doing the same thing over there, right? So that tells you that x1 through xn are eigenvectors. And we know that they were a basis because the matrix was invertible, right? X was invertible, so the columns are linearly independent, right? They were already a basis since the matrix is invertible. Okay, so that's the end of the forward direction and the end of the proof. Okay, so you see that our goal, in some sense, is to, you know, it'd be nice to find an eigenvector basis, right? Given a linear transformation, given a matrix, it'd be nice to be able to find an eigenvector basis for it, because then you know that the matrix was diagonalizable. That might not necessarily happen, but it would be nice if it did. And we've seen one case where it automatically does happen if you have n different eigenvalues, right? Earlier we said if you have n distinct eigenvalues, then you're guaranteed an eigenvector basis, and now we see that eigenvector basis guarantees diagonalizability. Okay, any questions? Anybody, anything confusing? Okay, let me point out now that this is actually stuff that you've seen before. So way back when we were doing matrix representations, linear transformations, we basically could have gotten to here in one move. Okay, so let me just connect things back to what we did before. So alternate viewpoint. Okay, so let's recall what we were doing before, right? Going from Rn to Rn, you have like left multiplication by some matrix. So A is an n by n matrix, right? And suppose, as usual, if you may recall, suppose we have a basis B. B a basis. Okay. And you remember what we would do, what we used to do a lot was this sort of thing. You would take some vector here, and then you would map it down to the coordinate vector with respect to that basis, right? And then you would get a matrix representation of it with respect to that basis. So I'm going to use the same basis on both sides. Okay, so here we again have the same coordinate vector map. Okay, and recall the coordinate basis, what was this called? Coordinate vector was constructed so that if you took b1 through bn and multiplied it by the coordinate vector, you would get your original vector, right? V was the linear combination of these guys, right? V was the linear combination of these guys with these coefficients. Okay, so in other words, VB was B1 through Bn inverse V. Okay. We have been calling this thing X inverse, right? This is what we're calling, this is what we've been calling X. This guy is X inverse. Okay, so so this map here is actually multiplying by X inverse. If we're going this way, it's multiplying by X if we're going this way. Okay, so okay, so what's the point? The point is that if these guys are eigenvectors, right? Then what's the matrix representation going to look like? You guys remember how to get the matrix representation, right? You look at what happens to each of these vectors, and then you take the coordinate representation, coordinate map representation, coordinate vector of it, right? So you would take A, you would hit the first guy with it, you get AB1. But AB1, right, ABI is just going to be lambda I BI. So suppose that the BI's are actually are eigenvectors with the standard notation for the eigenvalues. Okay, right? Then this is going to look like this, right? And what's the coordinate vector corresponding to that? Well, that's just going to be lambda I. It's going to be 0, 0, 0, 0, 0, lambda I in the ith place. Right? Because this is lambda I bi. It's 0, 0, 0 b1 plus 0 b2 plus blah, 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 plus lambda I bi. So its coordinate vector is going to be this.
The diagonalize.
Right, so in other words, the matrix is diagonal, right? So this thing is just going to be lambda 1, b lambda n. Exactly. Right? So what does it say? Right? If you have an eigenvector basis, then the matrix representation with respect to that basis is diagonal. This is really, I think we even said this, or we might have even mentioned this at the time, but this is the point, that as we just said, if we have an eigenvector basis, then ABB is diagonal. The matrix representation with respect to that basis is diagonal, right? And if we think about it, what that says is that if we go through X first, and then map through A, right? Go through X first, and then map through A, and then go through X inverse. That's the same thing as going through ABB, which is the diagonal matrix, right? Which is really ABB. Right. So it's exactly the same thing. Exactly the same thing. Okay, just to show you that, in fact, we actually knew all this already. Let me just do one small thing in the 2 minutes that we have left. Okay. Yeah, so the point is that we knew all this. We knew all this already. Okay. Okay, so let me just do one small calculation to show you like how one does this concretely. So here's an exercise. It's not an exercise. It's an example. You have a matrix 5, 6, -2, -2, and you're told to diagonalize it. Okay. So the first thing we do is we're going to find the eigenvalues, right? So we want to have an eigenvector basis. In order to diagonalize, we need an eigenvector basis, right? We need X, right? So that we can diagonalize with X. So we need to find, we need a basis of eigenvectors. Okay, so we need to find the eigenvectors, we need the eigenvalues. So we just take the determinant of, we need to calculate the characteristic polynomial. Okay, so P lambda, what we've been denoting as P lambda is going to be this thing. If you work it out, it turns out to be lambda squared minus 3 lambda plus 2, which turns out to be lambda minus 1, lambda minus 2. Okay. So you get that the eigenvalues are 1 and 2, which is a good sign because we've got 2 distinct eigenvalues, which means that we're going to be diagonalizable. So then we just need to find the eigenspaces, right? So for E sub 1, right, we want to look at 4, 6, -2, -3, right? Right. We look at, remember, we look at 5, 6, -2, -2 minus lambda 1, 0, 0, 1. right? And we're looking at the determinant of that. Right. So now we want to find the null space of this, right? Right. Well, this, right, so E1 equals the null space of this. Okay, but this thing is equivalent to, we can get rid of one of these rows. This is just 2, 3, 0, 0. Right? And so we see that, for example, so we see that we see that 2x plus 3y must be 0, right? And so if we take, say, x to be 3 and y to be -2, that'll work, right? So 3, -2, and so E1 is actually the span of 3, -2. Okay. Similarly, E2 can be seen to be the span of 2, -1. Okay. So if we take x to be 3, -2, 2, -1, and we conjugate a by it, what we're going to end up with is 1, 2, 0, 0. Okay. And that would be our diagonalization. Okay. So this is how you concretely diagonalize a matrix. You just find a basis of eigenvalues, eigenvectors, and then you use that to create your matrix, that you want to conjugate by. Okay.
The fact that the two, like the 1 and 2 are the two eigenvalues, is that a coincidence?
No, that's
part of it.
That's part of it,
Okay.
right? Remember that the diagonal matrix that you got
Oh,
had
yeah,
had the eigenvalues down there.
Right,
Yeah,
okay.
yeah. And if we had put these in a different order, then we would have gotten them in a different order. If we had reversed the order here, then we would have gotten 2, 1, say.
So could we in theory just stop when we get the eigenvalues,
Yeah.
or?
Our goal
You
is-
know,
Oh, okay.
so if somebody's asking, what does it look like? What does this matrix look like?
Uh-huh.
And you find that you've got these, when you diagonalize it, you could stop here. Yeah,
Okay.
you'd say, okay, I know what it's going to look like.
Yeah,
Right? It's going to look like this.
yeah.
So yeah, that's true.
So the eigenvectors are 3, -2, and 2, -1.
Yeah. Yeah. Or any multiple of them, right? Because
Sure, yeah.
Yeah,
Other
6,
like the
6, -4,
normalized
whatever.
ones.
Hmm?
But the normalized ones, because they're the smallest.
I just chose them actually. Yeah.
It's whatever that
Yeah.
makes it
Yeah.
the null space of the.
Yeah. Whatever gives you 0. Yeah. Okay. Okay, that's it. See you guys next week.